announce in 5 seconds.
Hello, dear professors, colleagues, and friends. I would like to introduce Professor Per Christian Hansen to present his talk, which is joint work with Silvia Gazzola and James Nagy. The title of their talk is IRcgls Iterative Regularization for Inverse Problems. Professor, please.
Thank you. Hold on a second here. Let's see. Can you still see my screen?
Not yet.
Not yet.
I was wondering how I can see you guys here, but anyway, I cannot. Anyway, let me start here. First of all, thank you very much for the invitation. It's very nice to meet new people in this day where it's so difficult to go anywhere. So I will talk about a Matlab package that we wrote a few years ago. So my interest is numerical algorithms for solving inverse problems. And I think that writing a package is one way of making numerical methods and algorithms actually available to a large community. So I like to write packages. And when I mentioned this to Sylvia and to Jim, they immediately said, yes, let's do it. Let's write a package here. So I will be talking about this package, the contents, and I will show you what you can do with the package. Okay, so for this audience, I probably don't really need to show this slide here, but I'm interested in discretizations of linear inverse problems. So we have a problem in this form here with an ill-conditioned matrix. So, and I'm going to introduce my notation here, you see. So the underlying model is that we measure noisy data. Now, the noisy data
I'm sorry, can you just share the screen?
I'm not sharing the screen?
No.
I'm so sorry. See, I am not very good at this.
Okay.
I'm so sorry. Thanks for stopping me. Does this work?
Yes.
Yes.
Okay, I'm so sorry. I'll go back here. Here's my first slide. Yeah, and there's a picture of Silvia Gazzola and Jim Nagy, right? And here's my first slide with the notation, right? So we assume we have noisy data that corresponds to a forward problem with an exact solution plus some noise. So whenever you see the X bar, that denotes the exact solution that we're trying to recover, and E denotes the noise. And of course, because of the noise, we cannot reconstruct the exact solution. We're trying to compute a good approximation to the exact solution. And because the matrix is ill-conditioned, the noise will be amplified very much. So we have to use some kind of regularization to get rid of some of the noise. As you can see here, the naive solution consists actually of the true solution plus what I call the inverted noise, right? So is when you deal with inverse problems, you need to regularize. So I'm particularly interested in large-scale problems. So that means that the dimensions of the matrix A are pretty large. So we need to look at iterative methods for solving these large-scale inverse problems, and that is what this software package is about. Okay. Just a historical comment here. My first software package was regularization tools. It was published in '94. I worked on it for a few years, and that was actually developed on a very old school computer that you can see there. So anyway, why are we interested in software packages? Well, I think there are many good reasons why software packages are relevant. For example, when you teach inverse problems and when you train people, it's nice to have a collection of different methods around. For here, methods, a collection of methods for a particular type of problem, and here that problem is inverse problems, and then you can try different methods. You can easily try to solve the same problem with different methods and see which one is perhaps best suited, or you can focus on one method and you can try to solve different problems with that method. So for those reasons, it's very nice to have a package around that includes both implementations of various methods and also some nice test problems that you can use. And of course, you can also use the package for actually solving some of your problems, right? And with the package, such a packet essentially makes life easy for you because somebody else spent time in implementing the methods and testing them. So so it's nice. So for that reason, it's also nice to have a method here. And I honestly believe that this is one way of actually getting a bit of attention for the numerical methods that we develop, that is to make them available. Okay, so here's the agenda for my talk. I will start with a brief overview of the package, and then I will talk about a few of the methods that we have implemented in the method. I cannot go through all the methods there, so I'll talk about Tikhonov regularization, regularizing iterations, but also something called hybrid regularization methods. And then I will finish with illustration of how some of the test problems in the package can be solved by means of these iterative methods. So that is the idea. Here's a link to where the software is available, and this is the reference to the paper. Right. This slide is about some of the considerations we had before writing the package, and I think it's always good to discuss that. What should be sort of the structure or the conventions for a package? And as you can see here, again, I have mentioned that it should be easy to use the package. So there should be no compilation, no need for additional toolboxes. You download the package and then you just use it, right? And at the same time, it should be able to, you should be able to interface to other packages. And we can do that here, for example, with a package with iterative methods for tomography. Okay, when you need to use one of the iterative methods, well, all the calls to the iterative methods have the same form, right? So there's some input, the matrix A, the right-hand side B, the number of iterations, and then some options. And then you get the solutions, and you get also a structure with information about the performance of the method. So if you want to change from one method to the other, the only thing basically you need to change is the name of this routine here. So again, to make life easy. And okay, another thing that I think is very important when you provide a package, there should be test problems included such that you can try these methods here. And so we have that, again, with the same philosophy that it should be very, very easy for you to generate test problems, right? And for the non-experienced user, you don't need to worry too much about the options. And if you are actually, if you have experience in this area, then you have full control of what's going on by means of these different options that you can set. Okay. So that was the philosophy here. And I think I'll give you here one example of what you can do here. A very naive and simple example, but it illustrates what we can do. So let's try to use the CGLS iterative method with the regularizing iterations to solve an image deblurring problem. So you see, you only need to write 5 lines of code in order to do an experiment. The first 3 lines essentially set up the test problem. You set up your relative noise level, and then you generate a test problem, which is image deblurring here. With speckle blur. Speckle blur is one way of simulating atmospheric turbulence. So it's something that arises in ground-based astronomy, right? And there you can see you generate a matrix A, you generate a clean right-hand side B, and the true solution X. And then in the 3rd line, this is where I add Gaussian white noise to the clean right-hand side. And then I set some options here in the 4th line. I say I want to use the discrepancy principle. I give the noise level, and then I run the CGLS method until that stopping rule is satisfied. And once I do that, I will get a weight bar on the screen, and after a little while, I will get my results. So here's a way to illustrate what I'm doing. The figure on the left is the test image. So that is the sharp image. The figure in the middle shows the noisy data. So that's a blurred image, quite blurred there. And then what you have on the right is the reconstruction computed by means of CGLS with that particular stopping rule. Okay, so that just illustrates how easy it actually is to play around with these iterative methods. So, okay, so what have you got in the package? Well, here's an overview, and I know that this slide is much too busy. And I'm not going to go through all this here, but you can see on the left that we have many different types of least squares problems that we can deal with maybe without constraints, with simple constraints here, with more complicated constraints, and we can also compute Tikhonov solutions here, again, also with or without constraints. We can compute sparse solutions here where we have a 1 norm regularization term. And then we have some other more experimental stuff here at the bottom that can do other things, right? And over here on the right, of course, you see the names of all these algorithms here, right? So that's an overview. And I know that's too much. And this is also pretty overwhelming, but this is an overview of the test problems that we provide in regularization tools. Such problems are very, very nice to test your methods. And basically what you can see here is that we have image deblurring with different kinds of blur, different types of point spread function. Motion blur, speckle blur, many kinds of blurring there. We have something called inverse diffusion. So essentially that arises from a partial differential equations. We have inverse interpolation. We have a test problem from NMR. And finally, we have a few test problems from tomography. So different types of inverse problems here that you can play around with. And in addition to that, we have a routine here where we can add different types of noise to the clean data, and we can adjust the noise level. Okay, and you will see later some examples of where we use these tests, some of these test problems. All right, okay, so let's see. Let me go a bit more into one of the routines. IRcgls is an implementation of the CGLS algorithm. So that's a Krylov subspace method, and essentially it's mathematically equivalent to applying conjugate gradients to the normal equations that you see here, right? But we really don't want to solve the normal equations very precisely. We just want to stop when the residual of the normal equations is small. Okay, so we want to do that. So again, how do we do that? Assuming that we have generated the matrix A and the right-hand side B, we just call IRcgls. Okay, and then we get two outputs from that. The first output X, that's an array, a 2D array, and every column of that array can hold all the iteration vectors, or in this case here, it will just hold the final iterate where your stopping rule stop the iterations, and that was the two stopping rules we use right there. Okay, and then there is the info structure with a lot of information, and for example, it will tell you how many iterations were needed. So that's probably the simplest call you can do. Just solve the problem, right? You can also say, I want to see some of the iterates. Okay, I may want to run 500 iterations, and I want to store every 25th iteration. So iteration 25, 50, 75, and so on and so forth. So you can input that vector here, k, and then it will store those particular iterations here in the array X here. Okay, all right. And again, you can use info to see when it actually stopped the iterations. And you can do even more here. If you want to go deeper into the settings, you can set a maximum number of iterations here. Okay, 500 corresponding to this one here. And you can also say how accurately do you want to solve the normal equations. So you can input that here. Okay, so there you can see going from something very simple to something much more sophisticated there, depending on your experience and what you want to do. Okay, so that was least squares problems, but you know, we are really talking about inverse problems here, and then we know we should not just naively solve the least squares problem. We really ought to perform some regularization, right? And here is the very well-known Tikhonov regularization method, where you minimize this weighted combination of a least squares residual and then a regularization term over here. And you have a regularization parameter here that controls how much regularization you want to impose. And in this package here, the matrix L can be an identity matrix, or it can be some approximation to a derivative operator. Again, this is something you can specify to the software, right? Okay, so this is one way, of course, to formulate the Tikhonov regularization problem. There are two alternative formulations. There is these kind of normal equations, and there is this formulation over here on the right, where you can see that this is actually just a linear least squares problem, right? And since the CGLS method was just designed to solve the linear least squares problem, essentially we just apply CGLS to this formulation over here in order to solve the Tikhonov problem with a given lambda, and that's how we do that. Again, some relevant stopping rules here, maximum number of iterations, and again here you can say I want to solve my regularized least squares problem to a certain accuracy, and again that is controlled by a parameter that you give as input to the software. Right, so let's see how that goes. Again, there are simple ways to do this, and there are more sophisticated ways. And just a very simple way here, assume that you already know a good regularization parameter lambda, and that you want to use a regularization matrix that is just the identity. Well, the only thing you need to specify is the value of lambda of the regularization parameter. You have to put that into options, and then you call CGLS with that option there. And then, since you haven't specified anything about the regularization matrix L, the software will assume that L is the identity matrix, right? And in this case here, there's no need to specify how many iterations you do, because we want to stop when one of these stopping rules is satisfied. The method automatically chooses max eta equal to 100. It's quite small, but that's in order to avoid that the code is running for a very long time and you get a little impatient there. So you can always change these parameters. If you want to try other things here, you can do that as well. Here's one example. If you want a regularization matrix L that is different from the identity matrix, well, for example, you could use the Laplacian. So that will give you second order Tikhonov smoothing, and you can say, okay, that could be the Laplacian in 1D or in 2D. And again, you can input that, you can put that into the options structure that you have right there. That's the only thing you need to do. You don't need to think about how do I discretize the Laplacian. The code already does that. You just say, I want the Laplacian, and you put that in the options, right? So that's one thing you can do. Another thing, if you're not happy with the L matrices that we provide, you can write your own. Or you can input a matrix L, or you can input a handle, a function handle that corresponds to multiplication with L or its transpose. So there are really many things you can do with this package here. Okay, let's see, how am I doing? Let me move on here to regularizing iterations. This is where I think it starts to get really fun. Okay, and I have already mentioned these regularizing iterations. So the underlying theory is the following. If you run CGLS for k iterations, well, that corresponds to actually solving the least squares problem with the constraint that the solution lies in a k-dimensional Krylov subspace, a particular subspace that I'm showing there. So I usually say that here you are doing regularization by projection. So this is different from, let me go back here. In Tikhonov regularization, you impose your regularization by specifying a regularization term over here, while in these methods here, you obtain the regularization by projecting onto a low-dimensional subspace. And for CGLS, this is the particular subspace that is used, right? So here is for a particular very simple test problem here. What I show you here are the orthonormal basis vectors for a 5-dimensional Krylov subspace. So you see that looks a bit like a spectral basis that has more and more oscillations as you go from left to right. And as a matter of fact, I also, for this simple problem here, I computed the right singular vectors that we use as the basis typically. And you see they are not the same, but they look quite similar. So this Krylov subspace actually provides basis vectors that resemble the SVD basis. So it's a way of kind of working with the SVD without computing a full SVD, but somehow working with the subspace that represents approximations to the SVD. And this is why this works. So in a sense, truncating these iterations after k iterations is a bit like you could say using truncated SVD. And of course, we don't get truncated SVD solutions, but you get something similar here, right? So then, of course, the challenge is to choose the right number of iterations. Right? How do you know that? And for that reason, we have various stopping rules. And since k now acts as a regularization parameter, the more iterations you do, the more components, SVD components you include, and hence the less regularization you're doing. These stopping rules are actually regularization parameter choice methods. And there's a bunch of those already that have been developed over the years, such as, generalized cross-validation, the L-curve criterion, discrepancy principle, and so on and so forth. So this is all well-known stuff, of course, and here's some early references to people who talked about these regularizing aspects of the CGLS method. Okay. Let's see. So how do we actually do that in IR tools? We will be using the discrepancy principle because it's easy to explain, it's easy to understand. So assuming that we know the noise level, and by that I mean the norm, we have an estimate. Let's assume we have an estimate of the norm of the errors in the data. You may or may not have that, but in some occasions you actually know pretty much how much noise is in your data. And then we can use this stopping rule here. So as soon as the 2 norm of the residual falls below the size of the errors, the norm of the errors, then you want to stop. There's no point in going further than that. That is the discrepancy principle, usually attributed to Morozov. And very often there is a little factor here, a safety factor, which should be just slightly larger than 1, just in case that your norm estimate here might be just a little bit too small, right? So typically there should be a factor there, but it should be close to 1, but a little larger than 1. Okay, so how do we do that in IR tools? Well, first of all, we in options, we say that the relative noise level is this number here, right? And then here, I really want to be on the safe side. So this safety factor here, instead of using the default value here, I want to use a larger value, 1.2, and the way you do that is by means of this line here. So you can say, I already have some options, and now I add this particular feature here to my options. So that's what I do. And let me show you an example how this works. This is a toy problem, a test problem from computed tomography. It's inspired by this cheese here. This is a cheese I bought some years ago in Amsterdam because I thought it was so wonderful, so colorful. So I had to buy that. So anyway, here are the iterations by means of CGLS. Okay, so what I'm doing is I'm reconstructing a slice of this cheese here from projections, from X-ray projections. Okay, and I show you the iterates here for 1, 2, 3, 4, and so on, iterations until 12 iterations. Right, and I hope you can see that as I take more and more iterations, I'm actually constructing a sharp image. In the beginning, up here, I only have a one-dimensional Krylov subspace, and really not very much is going on. This corresponds to a two-dimensional Krylov subspace, and 3 and 4. And you can see just after 4 iteration, I have actually captured a lot of the structure of the solution, even though I'm only in 4 dimensions. But of course, it's not a very good reconstruction. But as I do more and more iterations, I actually compute a pretty good reconstruction. You can see that there is a bit of noise here. There are some red pixels once in a while that should not be there. And that is, of course, because I have noisy data. So I cannot expect to do a perfect reconstruction, but it's actually pretty good and looks a bit like my Dutch cheese right there. Right. Okay. That was an illustration of what we're doing. We can do more fun things with the package. And when you're an algorithm developer, then sometimes you're interested in monitoring the iterations and monitoring the convergence to see what's going on. Does the method behave as expected? And for that reason here, this is I kind of like this idea here, if I may say that. In the options here, you can set something called no stop. You can turn that on. That means that the CGLS method will produce the solution corresponding to the stopping rules, but it will give you more. It will actually continue the iterations beyond the optimal point, so that you can check if there really was this semi-convergence that I talked about. And to do that, you also need to introduce the true solution. So of course, this is not something you can do on a real problem, but as long as you're doing experiments, this is a fun thing to do, right? And then you run your iterations, and then you get info. Info is a Matlab struct that contains a lot of information you can see here. Okay, too much to cover here, but one thing that you get out here is that you get the solution, the regularized solution that corresponds to the stopping criterion, but you get so much more because you also get, the relative errors and the residuals and so on. So let me just show you that instead. Okay. So here is a particular. Here I'm back to the deep blurring problem with 1% of noise, and I generate the test problem in these 2 lines here, and then I input the noise level here. So that's going to be my stopping rule is going to be the discrepancy principle. But I say I want to actually keep running the method beyond that point just to see what's going on. Okay, and I input the true solution here. I run the method, and then it tells me that after that, this stopping rule stopped the iterations after 33 iterations. That's when the discrepancy principle was satisfied. So this is where the method thinks it should stop. It also tells me that I would actually get the best solution after 39 iterations. But of course, this is something I can only do because I know what the true solution is. So that's kind of cheating. But then you know if the discrepancy principle was doing a good job as a stopping rule. And 33 is not too far from 39, so it was kind of all right. And then you can see here the output. You can see what is this here on the left. That is actually the norm of the errors. So you can see this is the number of iterations. And as you do more and more iterations, the error goes down. And then it has a minimum here at 39. and then the error starts to increase again. That's when you start, when your Krylov subspace is too large and you start including the unwanted noise, right? And what we have over here on the right, that is the norm of the residual. That is monotonically going down, and the discrepancy principle essentially means that you want to stop the iterations as soon as the residual norm is less than or equal to eta times the noise level, right? And that happens right here. So you can get, you don't have to work very hard to get these plots here. Again, this is something that the package is doing for you. So it's very easy to do these experiments. Let's see, how am I doing here? Right. You know what? I think I had planned to say something about hybrid, something called hybrid methods. And maybe we can return to that later if there's time. But I don't want to move on because I want to get to the examples using some of the test problems. But before doing that, I do want to mention that we have other regularization methods there. Of course, we have Tikhonov regularization in general form. This can be also accomplished by something called Priorconditioning that you can apply to the iterative methods here so that you avoid having a regularization term, and instead you use something called a prior condition. Right? It's very similar to a preconditioner, but it's, as you can see, it's changing the Krylov subspace. And there are other things you can do here. You can add non-negativity to the solution. And we have even more methods there to impose sparsity, total variation, and so on and so forth. Right. Okay. So, before I move to the test problems, I just want to say that I hope I gave you a little bit of an overview of some of the methods that are available and how easy it is to actually use these iterative methods. Now, let me move on here to the test problems here. The first test problem I want to show you is, again, the deblurring test problem that you have here. So when you specify that, which is what you will do again with n is the size of the image. And then with options, you have a lot of control over the test problem. For example, you can choose what test image you want to use. There are a number of built-in test images. You can also choose the point spread function that is the type of blur that you're applying to the image. And you can also specify a blur level, whether you want to do mild blurring or medium or severe blurring. And whoops, let me show you a few test images here. So on the left, you have 3 different test images. There's a satellite image, another image of the Hubble Space Telescope, and on top you have a simulation of stars. So yet an astronomical image there. And in the middle, I show you 3 different types of blurring. We have more than these. There's motion blur. That's essentially when the camera is moving. When you take the picture, we have shake. This is similar to motion, but that's when you actually shake the camera as you take the picture, and you get a more complicated blurring here. And then, of course, we have defocus when the camera or the telescope is out of focus. And what I show you over here on the right are the corresponding point spread functions. So anyway, these are all available in the package. So I want to move on. We have already seen reconstruction of these blurring test problems. So I want to show you instead an example coming from computed tomography, so X-ray CT. And we have three geometries available. We have parallel beam tomography, we have fan beam tomography, and we have spherical means tomography, and that indicates three different geometries. Remember that what you measure are integrals along. Well, in parallel beam and fan beam, you measure integrals along the rays, either parallel or in a fan configuration here. And in spherical means, what you measure are integrals along these circles here. So we have these three types of tomography. And again, you can control a lot of the geometry by means of the options input. Again, we have a number of test images available. In tomography, the test images are typically called phantoms, and we can generate various types of random test images that you can play around with here, with very different features. Here's a lot of high frequency information. Here, it's only low frequency. This is very smooth phantom here. We have something called grains that stimulates what you actually sometimes see in crystallography, and we have other types of phantoms as well. Okay, and I will show you here an example where we're doing fan beam tomography. Okay, so this is my size of my image is 256 by 256, and here. This is in order to get the fan beam measurement geometry that I mentioned. And here's the thing. I want to experiment with a situation where I do not have measurements all around the object, but only measurements in the angle range from 0 to 130 degrees. Okay, so I don't have a full scan here. I only have a limited scan. And you could say, why? But that's in some situations that is actually something you have to do. There might be something that blocks the object, so you only have a limited range. So it's a situation that occurs in practice. Okay, so what happens here is that I generate the test problem and then add some noise. And just to try something else than Gaussian noise, here I have multiplicative noise, which is more realistic actually for CT problems. Okay, so I generate my data B here correspond to a sinogram. If you're familiar with CT, the sinogram is something that looks like this. Okay, and let me try now to solve that problem here. And I'm using an implementation of the Kaczmarz method, also known as ART, algebraic reconstruction technique. And this is what I get. Okay, this is the solution that I get when I call that particular method here. You can see, again, I set up some options. I call ART, and then I show the reconstruction. Again, stopping the iterations by means of the discrepancy principle. So this is the solution that you get. And again, I hope you can see that it was pretty easy to set up a test problem and solve it by means of an iterative method, not very many lines of code. And I get this here. So you could say, isn't that a bad reconstruction? Look at that. Well, yeah, there are some artifacts, aren't there? There's like something missing over here. There are some strides, some lines here, and then it seems like something is missing here. But this is the best reconstruction you can do. It's not because there's anything wrong with the algorithm. This is what you ask for because you don't have a full range of measurements. You're missing some measurements, and when you do that, you get a solution that looks something like this. Okay. So trust me, it's actually pretty good. It's pretty good. But maybe you have to work yourself with CT in order to see that this is a good reconstruction. The last example I want to show, this is quite interesting because it shows a little more advanced thing you can do with IR tools. Okay, so this test problem is inverse interpolation. So what is that? Well, in some communities, this is called gridding. So what you have is that you have measurements of noisy data scattered like this, okay? So assume that here's a surface and these blue dots correspond to your noisy measurements. And you can see in the X and Y, these points are just scattered. So someone has measured this, but now you would like to go from these scattered points to points lying on a grid, right? Typically in interpolation, you go from the regular grid to something else. In inverse interpolation, you go from scattered points back to a grid. So that's an inverse problem for you right there, right? So we can experiment with that. So this is the data. This is a true solution. Okay, let's see if we can reconstruct that. So again, we generate the test problem like this, and then we generate it up here. And now I use CGLS once again to compute a solution. Okay. If I don't get any options here, the method will choose a regularization matrix, which is the identity matrix. And that's just not a very good idea for this problem here. I don't show you the solution, but trust me, it's not very good. But you know, I know something about this particular test problem here. I know that I want my solution here actually corresponds to a smooth function. So wouldn't it be a good idea to actually impose second order regularization by means of the 2D Laplacian and use that as a regularization matrix? So I'm going to be doing that. And you see, the only thing I need to do now is tell CGLS that I want to use this. I put that in the options. I put that here, and then I get this solution here. So again, this is my data, and this is the solution I get. So of course, this is not too bad. It's pretty smooth. And of course it is, because I imposed smoothness here by my choice of the L matrix. But there's something wrong with it, isn't it? Let me go back here and look at the exact solution. You see, the exact solution actually has a peak over here towards the back, right? And I don't get that. Why is that? That's because the Laplacian that is built into the package enforces zero boundary conditions. So I get a solution that wants to go towards zero at all four boundaries, but that's not really what I want. Okay, so on this last slide here, I show you how you can fix that by actually building your own regularization matrix, which corresponds again to the Laplacian, but with different boundary conditions on the different boundaries. So I want to enforce zero boundary conditions on 3 of the boundaries, and then I want to enforce a reflexive boundary on the last a boundary condition here on the last one. So sorry, it looks a little complicated. That's what I do here. This is where I create a regularization matrix that corresponds to these boundary conditions. And then I can plug that in, and this is the solution I get. And it's pretty good compared to the true solution. So you can see that you can actually do more sophisticated things than what is available there. And it also illustrates a point here that sometimes one should not just use default values. Sometimes it is a good idea to think a little bit about what it is that you want, and then specify your own options instead of using the built-in options. Okay, so let me finish here. My presentation of the software package here. So as you can see, we have many iterative methods available. We also have some fun test problems around, all of them 2D test problems. And if you're new to this area here, you don't have to worry too much about all the different options that you can use. You can just use the methods as they are, but if you are an expert user, then you actually have full control of everything you can do. So there are many ways in which you can use this package here. I hope some of you will be interested in the package. And if you are, you can download it and you can try it. And if you find a bug, please let us know so we can fix the bug. Thank you very much.
Thank you, Professor Hansen. Any comments, questions?
I have a question.
Go ahead.
Professor Hansen, thank you very much for the presentation. It was very interesting for me. Related to the next last slide, please, can you return to the...
That one here?
Yes, that's one.
Right.
You said that you changed the boundary conditions because your relations wasn't good. And how do you know when you can take appropriate boundary conditions?
Well, that's a very good question, because how do you know your prior information? It's almost a philosophical question, isn't it? How do you actually know your priors for an inverse problems? And sometimes you don't. Okay, right. The only way you can know that is if you know enough about the physics. If you know enough about the problem you're actually solving. The mathematics itself cannot tell you what is the right prior. So you have to know that. It's the same thing, but sometimes you do know. I mean, if you're doing X-ray tomography, and you're looking for little, if you're looking for a tumor, then your prior will be that you're looking for something small that is not supposed to be there. That's kind of your prior, right? If you are doing seismic tomography, then you know from geophysics, from geoscience, that typically the Earth organizes itself in layers, right? So that would be your prior there, that you will be looking for something that has layers, not necessarily horizontal layers, but it will have layers because you're going to have chalk, and then you're going to have something else, and then something else again. But it's something that must come from your knowledge about the physics, or somehow what you know about the problem. The thing is that if you don't know the boundary, let me go back here. If you don't know, and if you look at the residual, okay, the 2 norm of the residual for this solution here, which is not really a good solution, and if you look for the residual for that one here, those 2 residuals will be pretty much the same. So just from looking at the residual vector, you cannot tell which one is the right one. Okay. And that is, and what should we do about that? I don't know. I don't know.
You have to be deeply in that field, and you can feel if you have to adapt some conditions initially.
Right. So here's the thing. It would be interesting if someone could maybe use ideas from Bayesian inference and maybe machine learning in order to help guide this choice here of your prior. Mm-hmm. And we had a PhD student playing around with that, and she was not successful, I have to say that. So I'm not saying it's not possible, I'm saying it's difficult. It's difficult.
Thank you very much.
I have a question.
Yeah.
Professor Hansen, thank you very much for the nice talk. I think, I mean, the examples in this presentation focused on focused on tomography and some images. I was wondering if we can apply this package on for regularizing the solutions of inverse source problems, for example.
Well, here's the thing. Maybe the answer is yes. Maybe. Let me go back here. So what the package is doing is essentially, right, dealing with AX equals B.
Yeah.
So whenever you have a linear problem that you can write in this form here, then it's possible, and A can be a matrix or it can be a function, you know, that evaluates matrix vector multiplications. So let's see, in inverse source problems, that is that's a PDE, isn't it?
Yes.
Right. And is it if it's a nonlinear PDE, then you would not be able to use this package here.
I see.
But sometimes when you solve non-linear problems, you do that by a sequence of solving linear problems, and these linear problems may use some regularization. So maybe you could apply the package to these to the subproblems in the iterative process. Maybe, I don't know.
I see. I see. Mm-hmm. Thank you very much for the answer. I'm looking forward to research for that.
Very good. Very good. Mm-hmm. Yeah.
Any others? Comments, questions? So thank you, Professor Hansen.
You're welcome. You're very welcome. Thanks for giving me the opportunity to do a little commercial for my software package. It's very nice meeting all of you.
Yeah, nice to meet you. Thanks so much.
Thank you.
Thank you.
Yeah.
See you next time.
See you.
Bye-bye.